Hi, I'm Peter Harrison, and welcome to my talk for Reef Futures 2021. My talk is about optimizing mass larval supply and recruitment for successful larger-scale coral and reef restoration. This involves capturing coral spawn, culturing larvae on the reefs, and targeting the delivery of those reefs onto degraded reef systems. We're all aware of the global coral crisis caused by increasing chronic human impacts interacting with severe natural disturbances that are overwhelming the natural resilience of reefs and causing breeding coral loss and therefore impaired or no natural larval recruitment. We're all aware of the scale and types of impacts caused by humans, and what we urgently need to do is to start to restore coral communities at larger scales while there is real and effective global action on climate change. Sexual reproduction has significant advantages for upscaling restoration. There is cost-efficient collection and culture of hundreds of millions of genetically diverse larvae, increasing genetic diversity from resilient broodstock, co-culturing with symbionts and probiotics to increase larval survival and post-settlement survival and growth, and mass production of larvae and delivery directly onto reef systems. There are 4 phases of the larval restoration process: capturing coral spawn and slicks, mass culturing the larvae in reef pools, targeting the delivery onto degraded reef systems, and monitoring long-term survival and growth, at least to reproduction. This talk is focused on 2 aspects. I'm briefly going to talk about the many small-scale larval restoration trials on different reef systems, and then examine ways in which we're scaling up the mass larval production for larger scale impacts into the future. I first thought about the larval restoration concept after witnessing the first major bleaching event on the Great Barrier Reef in 1982. The Australian Centre for International Agricultural Research enabled funding for me to work in the Philippines with colleagues, particularly PhD student Dexter de la Cruz. The Philippines, like many reefs around the world, have many degraded reef systems, but good recovery potential. And therefore, Dexter did an initial pilot study, which was published recently in Scientific Reports, where he supplied about 400,000 cultured larvae into reef plots directly, and then examined their long-term growth and survival through to reproductive size at 3 years. After 3 years, there were about 2 colonies per square metre on the larval plots and none in the control plots, with an average cost of about $21 per colony. This was the first example of direct larval reseeding onto badly degraded reef systems. The restoration colonies are now dominating these reef sites, and we've continued to monitor the outcomes, but in the control sites where larvae were not delivered, there's no obvious recruitment, consistent with very low natural larval supply, and therefore these reefs are unlikely to recover without active restoration. The second pilot study was done on a different species, and that was published recently in PLOS One. About 300,000 larvae were supplied into the restoration plots. There was the typical type 3 survivorship curve, and after 3 years, about 1.8 colonies per square metre and a production cost of about $35 per colony. I then followed up with a high-density larval experiment using Acropora tenuis larvae derived from the spawning of the 3-year-old F1 recruits and some wild colonies. We supplied high densities of larvae under mesh tents onto degraded reef plots and compared them with controls. Very high larval settlement rates in the larval enhanced plots, just as predicted, and none in the controls. Typical type 3 survivorship curve, but rapid growth of the surviving corals once they grew to visible size. There was record growth to reproduction for the larger colonies after 2 years, and by 3 years, most of the colonies had become sexually reproductive, therefore re-establishing a breeding population on the degraded reef sites. After 3 years, there were significant increases in coral cover on the larval plots compared with controls, and very high densities of coral colonies and a production cost of about $17 per breeding colony. We also monitored the changes in the fish assemblages associated with the restoration process, and not surprisingly, found increased abundance of ketodontids and damselfish that were using these new habitats. I then took these processes to the Great Barrier Reef to start to examine other aspects of restoration, and particularly in that first experiment in 2016 at Heron Island, we're examining 4 different larval density effects. Not surprisingly, the outcomes from this were that we found that larval density drives settlement and recruitment patterns, so that the highest rates of settlement and recruitment occurred in the medium and high density plots. After 5 years, just a couple of weeks ago, we examined those colonies again after 4 years of monitoring and found that the larger colonies were reproductive. So we've re-established a breeding population of Acropora spathulata as a result of the larval restoration processes. This is great. It shows that we can be successful at small scales in many reef trials, but we need to scale up this process to have meaningful impacts at larger scales. The first phase of this consists of larger scale capture of coral spawn and slicks. The predictable coral spawning on many reefs around the world allows us to collect millions of embryos for mass larval culture. In 2016 to 2018, I started some innovative spawn catcher ideas. We started initially using low-cost bamboo frames, then added some inflatable spawn catcher booms to allow very simple collection of many millions of eggs after the spawning events there. This was then scaled up on the Great Barrier Reef through a series of new projects with different colleagues and funding partners, to the point where we got to much larger scales of reef capture of the coral spawn using paired 30-metre booms, collecting hundreds of millions of eggs in the spawn catchers. More recently, I've been working with Matt Dunn-Babin from QUT using robotic collection to increase the scale of capture. So we're now routinely collecting tens to hundreds of millions of eggs and embryos during these spawning events. We then take those embryos and put them into larval culture pools. And again, what I've been doing over time is increasing the scale and the effectiveness of the mass larval culture process, from early smaller scale larval pools in the Philippines through to very large scale pools on the Great Barrier Reef, including the 13-metre octagon, capable of rearing hundreds of millions of larvae. The final phase of the process is the targeted delivery onto degraded reef areas. So after about 5 to 7 days larval development, the competent larvae are delivered onto reefs, either in mesh sheets, through pipe networks, or directly from the reef pools themselves. And more recently, again, working with Matt Dunn-Babin with an underwater robot to deliver larvae over many hectares. We're also working with citizen science to enable scaling up, to enable many different groups to start using this larval restoration process in the future. And there are 2 new projects that I'm currently involved with: the Reef Restoration and Adaptation Program, co-led by myself and Chris Staropoulos from CSIRO, and the new Paul G. Allen Family Foundation project called OptiCorals. So in conclusion, we know that many reef trials have shown mass larval restoration is successful, even on highly degraded reef systems, enabling us to restore breeding populations within a few years. We're scaling this up by focusing on multi-species coral spawn slicks to produce billions of larvae with additional robotic delivery, and therefore aiming to scale up from hectares to larger kilometre reef areas in the future. Overcoming juvenile coral loss is a big process. It involves a combination of producing more larvae, increasing the quality of the larval through larval nutrition, and selective breeding to maximise enduring success. This has great application in future to many coral and reef restoration areas in many reef areas around the world. So if you're interested in knowing more about this process, please contact me. And finally, thank you to the many people who have enabled this and the many funding and partner organisations who have helped support this work. Thank you.